Okay, I am officially recording. Today's date is October 9th, 2018. And in lieu of the lecture that was supposed to happen yesterday, Monday, October 8th, for IST659, I am doing two series of video lectures due to an illness that I don't want to expose you all to. So today I'm going to be primarily focusing on the material and understanding the concepts related to SQL, which is the topic we'll be covering today. And tomorrow's video lecture will be focusing more on actually scripting or writing SQL statements in a database. So again, today is focused on primarily running through the actual lecture, and then tomorrow we'll be focusing on implementing those SQL commands into the database. Any questions for the two on the call? Great. Okay. So like I mentioned, today we're focusing on SQL, which for me is the most exciting piece of this entire class. This is a really robust and versatile language that not only can database administrators or DBAs use, this is something that analysts, something that economists, something that mathematicians can all use in order to analyze data that's stored in databases, right? So it takes more than just actually building out the database. A lot of people interact with SQL in a way such that there's an ability to actually query things and return information. Now, there was a question. Yes, I may have said that there will be also an additional class on Thursday. So let me see how far we get today, tomorrow, and I will also determine whether or not we need an additional session on Thursday. But thank you for your question, Chief. Okay, so jumping in today, obviously following normalization last week really rounded out all of the necessary information that we needed regarding modeling of data. So if you'll recall, by the time you get to third normal form, you've reduced a lot of that data redundancy, and you've found yourself now with a coherent data model that will be somewhat easy to maintain and will be really easy to translate into an actual database. And for purposes of class, we're going to be focusing on the Microsoft SQL Server environment for actually developing and writing SQL statements. Now, you can also write SQL directly in Microsoft Access, but that's not really why it was built. It was built more for the non-SQL non-SQL savvy person. Excuse me. I have a big cup of tea, so I'm going to drink it real quick. Microsoft Access was built for a non-SQL user interface. A lot of it's click and drag. You've all gotten very familiar with how to use the interface. But Microsoft SQL Server is much more enterprise-worthy and is pretty standard in a lot of Microsoft shops. Excuse me again. Okay, I will really try to limit my coughing. So with Microsoft SQL Server, we'll be able to actually create tables, create relationships, and all of the things that we did in modeling and Access, but we're going to be doing them using the SQL interface and SQL scripting language. And that's really what we're going to be focusing on today. So if there are additional questions about normalization that we covered last week, obviously they should have, we'll work them out as we go along. But if you have additional questions about normalization, please reach out to me or Nishita during office hours or through email. So the concepts that we're going to be focusing on today will be the SQL schema. Oh, my dog is jumping on me, sorry about that. The SQL schema and what that means in how to create databases, create tables in a database, and how to relate those tables to create a sort of a diagram or a relationship model amongst those tables and data values. In addition, we're also going to figure out what's the sequence of generating tables, right? So when we have these different constraints with respect to foreign keys, primary keys, minimum and maximum cardinalities, certain, I guess, logistical, hiccups can occur if you perform particular updates, deletes, or create statements among tables that have dependencies on other tables or attributes that have attributes that have requirements as a foreign key, such that they have to exist as a primary key in another table, there are certain logistical sort of sequences that need to occur. And then by the end of today's lecture, the expectation is that you'll be able to create tables, drop tables, insert values into tables, delete those values from those same tables, and in addition, change table schema. Now, that last one I think is going to be a little bit more complex, so I'll really try to do my best to focus on particular aspects of that area as well. Great. So before we get into actually what SQL is and why we're using it, here's a brief history of what SQL and where it has come from. What is SQL and where it's come from? You'll also notice by my dialect that I'm calling it SQL. In reality, I would say it's about 50% people call it SQL, 50% call it SQL. Both are perfectly fine and acceptable. Excuse me. Both are fine and perfectly acceptable. It was originally called SQL when it was developed using this system called System R at IBM in the mid-70s. But then it became a backronym, or it was first an acronym, and then it sort of reversed itself into later creating what it meant. So after the fact, it was SQL stands for Structured Query Language, but initially it was just called the word SQL. Now, SQL itself and sort of the, sorry, not SQL, but the relational database model was initially developed by E.F. Codd. E.F. Codd is sort of the grandfather of databases, and he's effectively, he's the person that's most often referred to as sort of the founder of database and those types of relational logics in reducing data redundancy. Before E.F. Codd came along, most programs or database systems were all reading off of flat individual tables without relationships. This had a problem in the sense that data was not easily shared from one application to another because there was no metadata or uniformity about how the data was defined. And in addition, the same problems that we faced with having to normalize the data, those update, insert, and delete anomalies would all have occurred to those exact same tables, especially in a non-modern technological workplace. So, for instance, if you had to update a single record or data point in a sheet that lived with respect to one of these applications in the 70s, maybe we're talking about NASA. NASA had to update, I don't know, the constant for gravity. Well, suddenly they have to update the constant for gravity in a lot of different places. There is no unique place where that exists in the database. Instead, it exists as a variable or a parameter in many different equations or sheets. So not having the ability to have a uniform data structure, obviously E.F. Codd saw the need, and he went ahead and developed this relational data model concept. In the late 70s, Oracle, everybody's heard of Oracle or Larry Ellison. Oracle is a huge technology company whose backbone and foundation is in database management, SQL, and other enterprise technologies like ERP. So Oracle today is known as sort of like I don't know, I can't find the word right now, but uniform or omnipotent technological company that can usually kind of find its way into almost all aspects of business. But originally, it was really focused on database management with respect to implementing SQL. It was effectively the first I guess, competitor to IBM's implementation in the 70s. Now, starting in 1981, SQL and DS, which stands for, I can't remember what it stands for, to be honest with you. So SQL first became available in RDBMS, which stands for Relational Database Modeling Systems, on MS-DOS and VSE. Similarly, I don't know what VSE stands for. We can do a quick hiatus and look it up after this session. In addition, in 1986, ANSI, which is really famous for standardization of languages. So most popular languages, either open source frameworks such as something like JSON or YAML for file configurations. A lot of these are overseen in a national standards way, even HTML, for instance. ANSI sort of controls a lot of these standards. and ANSI adopted SQL in 1986 as part of that standard, I guess, corpus of different languages and protocols that they maintain in order to create things like uniformity. So if one company wants to interact with another company, it really helps to have uniformity. Similarly, in the job market, it doesn't help anyone that a person learns a very specific niche language for one company and then has to go and learn another one for a different company. So having a standard language faculty is really important, especially in the modern technological enterprise. And then, as you can see here, here's a list of major ANSI standard updates. Think of these as feature improvement, or I guess improving quirks about the language, not about the implementation, but just about how the language itself is structured in terms of clauses, which is something that we'll touch on later on in this lecture. Now, I say that it doesn't actually touch on implementation because every different DBMS handles the implementation of SQL differently. So for instance, Microsoft SQL Server will take in the high-level SQL that you've written, which is very procedural and documents exactly how you would like the data to be exported to you. But what's nice about SQL is you do not have to, I guess, tell the database how you'd like that data to be handled, compressed, analyzed, aggregated, any of that. That's all handled by the DBMS. So for instance, many DBMSs actually take SQL and sort of break that down and actually compile it down into C code. So the C code is actually underpinning the DBMS, is pulling the data from these files, aggregating it, analyzing it, and returning it back into either the visualization software, which a lot of the DBMSs have, can expose it in a website, or it can expose it in say a file as an export. And then lastly, current SQL is supported by almost all major database vendors. There are obviously a few exceptions, especially in the modern age when we get into things like NoSQL or other, I guess, large database systems that aren't based on SQL. But for the most part, if it's a relational data model, I myself personally have never come across one that's not SQL friendly. And another thing to know is that SQL has something called dialects, where particular quirks or nuances about the language can be slightly different from one enterprise service offering to another. So let's say Oracle might have a particular SQL syntax, which is slightly different than, say, I don't know, Postgres, which is an open source database architecture. Those differences, generally speaking, with small tweaks, can be resolved, but sometimes you can't take a SQL statement from one environment and easily port it over to another without having to make some small changes due to syntax. But what the heck is SQL, man? SQL stands for Structured Query Language. But why? Like, what is it, and why are we using it at all, right? Think of it like a standard language, and it's very logical in the way that it sort of approaches. So if anyone has ever taken logic, you have sort of if-then statements, right? You have your object, you have your action, and then you have your subject. SQL is similarly developed, right? You have your clauses, right? You have a select clause, which indicates what particular columns from which particular tables you'd like to be returned as an output of the query. You have your from clause, which indicates which tables you want to query the data from. And then lastly, you have your, but among the many clauses there are, an important one is the where clause, which indicates what particular filter criteria do you want to apply on the data as you're returning it back from the query. So SQL is simply a language that's shared by almost all DBMSs and definitely by all RDBMSs, which again is the relational database model. And the query itself is written by specifying the form of results declaratively. Therefore, by the results of the way that it's written, like I mentioned earlier, you don't have to worry about how the database is going to handle your SQL statement. As long as it's ANSI compliant in the way that you've written and it matches the syntax of that particular database management system, everything else is sort of magic to the end user. Let's say Microsoft has poured probably millions or billions of dollars into the way that SQL Server optimizes particular queries, indexes the values, creates temporary tables, or even does filtering or sorting. All of that stuff is happening behind the scenes, and it should be generally independent of the way that you approach the way that you write SQL. Obviously, there's particular SQL statements that are more or less efficient than others, but I think that is probably more for the advanced lecture outside of the scope of this course per se. In terms of the SQL environment, there are generally 3 types of SQL statements. You have your standard DDL, which is data definition language. This defines what a table looks like. This defines the indices or views that particular database or table can have. An index is a particular choice is a choice that the analyst or database administrator can make about how the data should be pre-sorted or pre-arranged to optimize the return state of the queries that you actually send to the DBMS. And similarly, views are pre-existing, let's call them materialized instances of data that are not stored in a distinct table. So I think I might have alluded to this early on in this program, but at the end of the day, database tables are files. So a view is sort of like a logical mesh that lives on top of files that simply points to where particular data lives. But for the end user, so the someone that's actually writing SQL statements, it looks just like a table. It doesn't look like anything else, and should behave just like a table would as well. And then similarly in DDL, you can also define keys, right? So you have your foreign keys, your primary keys, and how one table can relate to another. All of the data modeling that we've been doing up until this point will be done in DDL. And then we have DML. And DML is really, for me, composed of 2 different segments or sects of, I guess, SQL analysis. One is actually manipulating the data that already exists in a pre-populated table. This would be inserting, deleting, or updating it. Inserting it means that you're adding new rows to an existing table. Deleting means that you're actually removing rows from an existing table. And updating means that for a piece of information that exists in the table already, you're updating it in place, or you're changing the value in place. And then lastly, we also have the common select aspect of DML. Now, selecting data from a database is what, for most people, 99% of what they'll ever be doing. And in fact, most people who have read-only access to a database, this is the only thing that they'll be able to do. So if you need to fetch data from a database, if you need to run a query for sales, for a sales report from that your boss has requested, you're going to be doing that using the select logic in DML. You're not going to have to do table creation. You're not going to have to index. You're not going to have to create views. You're simply going to use select some columns from some tables. Obviously, it gets more complex than that as you incorporate things like joins or group bys or aggregations. But select SQL sort of has a ceiling to how complex it can really ever be. And then lastly, we have this other thing called data control language. To be completely frank with you all, DCL is something that's primarily handled in the graphical user interface, or GUI, of the DBMS. So for instance, we'll see in SQL Server that anytime you want to add a new user, you can script that as a command. But in general, I think it's just as easy to use the graphical user interface the way that we did with Access in creating the data models and querying. You can do something similar in DCL. So DCL is really geared more towards the database administrator, the DBA. For instance, if they wanted to bulk administer particular users to have access to the database, it's probably recommended that they use DCL. Okay, like I mentioned in the beginning of this lecture, we're really going to be focused mostly just on the material today. So anytime that my slides indicate, oh, let's jump into SQL Server, I'm going to save that for tomorrow. I really want to focus today on the material, and then tomorrow on the reinforcement of that material after I've posted this lecture back to Blackboard. Okay, so what you see in front of you are 4 related tables. I think we've seen many of these in the past, and what we're looking at here are how a customer purchases a product with respect to a particular order or a basket. Now, this is a common thing that we've seen before. We have 2 associated entities. You have the order and order line and entities which relate customers to products. And in addition, we want to figure out how we can model this in a database, right? How do we go from ERD to tables in a database with foreign keys, minimum, maximal cardinalities, things like that. I'm going to take a quick pause because I have a question. Okay, so Chi tried to connect with the SQL server, and it failed. Chi, what we'll do is we will tackle this after I've done recording this lecture, if that's okay with you. Very good. Where was I? I was saying, so the first thing that you should do is we have 4 tables, and obviously there needs to be some sequence by which we create these tables. So thinking about the different constraints that we have among primary keys, foreign keys, if we were in class, I would ask, which one do you think should come first? Chi or Min Yang, I know that you're both on the call. You're welcome to answer. Do you think that we should load tables that have foreign keys first or second? You are not obligated to answer, by the way. Okay, I will take your silence as non-answer. That's perfectly fine. So what we want to do is we want to actually figure out what are the constraints on the data. So for instance, if you have a foreign key in a table, that means there has to have existed an existing primary key in another table. Tables are entities in this use case. So for instance, if we look at the order table, notice that we have customer ID as a foreign key. So if we went ahead and created the order table and established the customer ID as a foreign key, the table would already be consistently, I guess, inconsistent because there is no associated foreign key or primary key associated with the foreign key in the order table because we haven't yet created the customer table. So with that in mind, that same logic can be portrayed over to the order line, which takes the order ID and product ID as foreign keys from the order and products table. So we can't actually cast them as foreign keys until the order and product tables have already been created. So for me, I think what makes sense is actually looking at, oh, pardon me, there we go. So we're going to figure out what that order is. So the first thing that we want to do is we want to create tables that don't have any foreign key constraints on them. So for me, when I look at this data model, there are 2. And you can tell by the fact that they have no foreign key IDs in their schema. So customer and product are both foreign key, customer and product are both entities without foreign keys. Therefore, we should create them first. And again, I reiterate, we're doing that because there are no existing constraints in those particular attributes and keys when we want to put them into the database. Now, similarly, once we've created those, then we can create entities with foreign keys. So again, it's very sequential. Now, the order of operation, the order of creation of customer or product is independent. It does not matter which one you create first, since there are no constraints on one or the other, or one and among them. So that order doesn't matter. It's really just the order of whether or not it has primary keys, whether or not it has foreign keys, and whether or not the table which contains the foreign key as a primary key has already been created. So for instance, order line may not be able to be created until order is created, and order cannot be created until customer is created. So order line is actually dependent on 2 additional tables being created first in the sequence for which we are creating these in the database model. I'm sorry if you hear a meowing in the background. I also have 2 cats among the dog that I also have. Can you please stop? Thank you. Okay, so great. So here are the steps in very plain English, not writing any SQL quite yet, what we want to do when we actually create a new single table, right? So first we want to define the table name. Now, what's very common among sort of database practice is the entity should be singular. Obviously, if it's an entity that has both a singular and a plural name to it, like fish is both plural and singular, you keep it as fish. But for the most part, keeping things singular is the best way to represent an entity. So for here, it's order line, not order lines. So that would be the table name. In addition, you're going to identify the data types for each attribute. So here we have char, which is short for character. and represents string values or alphanumeric text. So it could contain a name, it can contain a number, it can contain a combination of name and number. Those things all fall within the char data type. And then for quantity, we have an integer. An integer is a whole number value between negative infinity and positive infinity. And I'm confident that a database has a limit to the length of an integer because you have something called an overflow. But off the top of my head, I don't know what that length is, nor do I know how each DBMS handles overflow. Third, we want to identify which columns can or cannot be null. And if you'll recall, that is the same idea as having optional or mandatory attributes. So an optional attribute is something that can have nulls, and a mandatory attribute is something that cannot be null ever. And in addition, if you have foreign keys, the foreign key, if it's a composite primary key, cannot have nulls because it's part of the composite primary key. And a rule about primary keys is that no value can never be null. Next, you want to identify what the primary keys are. So how do I look at this table and know what the primary keys are? Well, ideally, you've already kind of created your schema ahead of actually loading this to the database. But here, you remember that a primary key has to represent a unique record or a unique instance of an entity. So here, a unique instance of the entity order line would be the combination of order ID and product ID. Lastly, next you want to determine if there are default values. So nothing in this table indicates that there needs to be a default value. But default values are common, especially if you're using something like time series data, and it matters when you load into the database, or if you know that 99% of the data that you're loading will all be of this one type, or this one specific value. And otherwise, for that 1% of the time, you have, let's call it edge case logic that implements a different value in those instances. Next, we're going to identify those constraints. So specifically, whether or not they are value. These come a lot out of the. These are coming from sort of the additional business logic or business constraints that you implemented when we were modeling the data. I'm going to sneeze. Pardon me for a second. I lied. I'm good. So identifying constraints on columns. So this can be anything that's domain specific, and by domain specific, it means that the order, the order line here might have a domain specific thing that the quantity can never be less than 0, and you would implement something like this in order to sort of enforce data integrity. So having a quantity of 0 or less than 0 in an order line would perhaps mean something like a return. But if that's not the purpose or intent of this entity or table in the database, then it should definitely have a constraint that says never less than 0. This would prevent sort of a bad data update or someone ingesting data into the database that was either incorrect or wrongly associated to this particular order line table. And then lastly, once you have all those pieces of information, you want to actually create the table and the associated indexes, usually all at once. Very good. Okay, this is the first SQL that many of you maybe have ever seen. So I will do my best to sort of describe it. So in the upper right-hand side, we're going to start with the customer table. Now, in this particular data model, the customer table only has 2 columns. The customer ID, which is acting as the primary key, and that particular data point or attribute has the data type of character. And inside the parentheses is the default length of that character. So here, the character is, here the data type is character, which means it's alphanumeric, and the length is 10. Now, if you tried to put a piece of data into this database with a length greater than 10, you will get an error. If you put something with a length less than 10, you will not get an error. What's inside the parentheses is sort of the maximum amount of the value. Now, now that I'm looking at this, I realize now that I don't necessarily know off the top of my head what the difference between char and varchar is, simply because I never use char. I always use varchar. So bear with me for a quick second while I bring up an amazing resource called W3 Schools. So this is actually a perfect segue for me. W3 School is very useful in looking up or Googling SQL, although their search is lackluster. Let's see if I can do W3 Schools, what's it called? Char. See if I can get you a better definition of char. Number code 65, not helpful. All right, let's see if, let's do data type char. You know what's great about doing this remotely is I wouldn't be able to Google something on the fly, probably because it would be inappropriate, but let's take a look at how char is handled versus varchar. Ah, okay. So char somehow pads with spaces versus varchar, which does not use padding. Okay, cool. So for some reason, if you wanted to use char, it pads the actual alphanumeric text versus varchar, which stores it just as is. And why one would do that versus not really would be domain specific. I have a so great question. Case sensitivity. It really depends on the database implementation. So, for instance, SQL Server is capitalization agnostic, or that means that you can search or input lowercase and uppercase, and it will treat them the same. However, Postgres is actually capitalization specific. So, if you wanted to query a column name, let's call it customer ID, if you put it in as capital C customer and then capital ID, it would not return. It would throw an error. It would say customer ID does not exist. And that's because you have to type it in exactly as it exists with capitalization. So it really depends on the particular DBMS. Great question. Okay, so with respect to customers, again, we have the char data type, which is a padded text, and varchar, which is an unpadded text. And by padding, I mean they're adding physical spaces before or after the text, specifically before the text, so that anything you put in there, even if it's 3 characters, will always be a fixed 10 characters in length. And to be honest with you, I cannot tell you why that would be good or bad. I think that's more to the database administrators in the room to be able to answer that one. Okay, so knowing this particular entity at the top, we're actually going to create a table. So you'll notice here on the left-hand side, we have a create table command. Again, this is DDL, database definition language. So the DDL here is the create table statement. So what I'm going to do is I'm going to walk through this and tell you which ones are SQL keywords and which ones are objects that you're either manipulating or are, I guess, part of your database schema. So here, create and table are both SQL keywords. Because you can create things that are not tables, therefore the create is its own keyword. Table indicates the particular object type that you are creating in the database. And customer here is actually telling it that this is the name of the table. Here we're actually saying that customer is all lowercase, and again, it's not plural. It's not customers, it's just customer. And then inside the parenthesis, you're actually, think of this as the table name, and then these will be the attributes. So the attributes here are the customer ID. So again, this is an object that you're creating as a field or a column in the table customer. You're articulating that the data type should be char with a length of 10. And you're indicating that it's the primary key. Now notice that these two are, again, keywords in SQL, primary space key. You can have something foreign space key, but here we want the actual primary ID to be customer ID. And it's really important that each attribute that you input in the create table is comma separated. So we have, again, customer ID, comma, customer name. And now note there is no comma after customer name because it's the last one. So when you write an English sentence, when you separate multiple values in a list, the last value, it does not have a following comma. Same thing for SQL. So we have customer ID, comma, customer name. Customer name is a varchar character type with a length of 30. So again, varchar is a SQL keyword. And then last we have not null. Not null is the same as saying over here that customer name is a required attribute. Similarly, you could just have the word null, which would mean that it's an optional attribute. But because we want every customer ID to have a valid customer name, we indicate that it has to be not null. And null in SQL terms means, I guess, missing value or no value available. And it's different than, say, an empty string. So here are some of the things that I mentioned. I actually did mention that last one. You'll notice here at the end, it's a semicolon. Now, depending on the syntax, semicolons can help you or hinder you. For SQL Server, semicolon indicates that it's the end of a statement. But I think for Postgres, you have a semicolon, it tells the interpreter to stop actually executing further SQL statements. So here, this is simply telling SQL that this is the entire create table statement, and we're done because we put a semicolon. The same way as an English sentence, you know that the sentence is done when you have a period. Here, you know the sentence is done when you have a semicolon. Now, all right, so now we've created this customer table. Maybe we don't want it anymore. Maybe we want to get rid of it. So in order to delete a table, remember delete is one of the words that we learned earlier with respect to DML, database manipulation language. In order to kind of separate out those two, they created a new word called drop. So in DDL, in order to remove a database from the in order to remove a table from the database, you need to drop that table. You do not delete the table. You drop the table and you pass the name of that table. Now, you can have different object types with the same name. That's perfectly fine in many SQL DBMSs. So here, we're actually indicating that you want to drop the table called customer. So perhaps you also had a view called customer. You would want to indicate here that you want to drop the view called customer. But because we're creating a table, as we did up here, we're only dropping the table that we've identified as customer. And again, it ends with a semicolon indicating that there is no more context or syntax to this particular command. And now, like above, we have this create table for the customer. We have another create table, and this is simply an alternative way to define the primary key. I personally prefer the first way since it's more succinct and it's, I guess easier to read. But alternatively, you can indicate, so look at just the top two lines for a moment. You have customer ID, which is a char 10, and you indicate that it's not null. Now, remember, when you had the primary key up here, you didn't indicate anywhere that it was not null. That's because a primary key can never be null. It's inherently embedded in the definition of a primary key. Now, similarly here, if you do it in this alternative fashion, you actually have to indicate that the customer ID is not null. Then you have a comma, which separates the additional attribute. And you have customer name, which is varchar 30, also not null. And then now notice that you have an additional comma. Now we're not putting in a new attribute, but we're simply indicating there's more to this statement. And the reason that we've actually indented here is I think it would interpret it even if it was left justified, but we've actually indented because we're adding an additional constraint. So we're constraining or restricting particular values of the customer PK on customer ID. Now here we're creating something called a primary key object, and it's called customer underscore PK. So there's a new object being created here. And specifically, the customer key here is acting as a function with the value being passed as customer ID. I'm going to take a question. One moment. What should we do if you want to drop customer name or drop customer, if you want to drop customer name from table customer? Great question. So again, the drop is only for Oh, you know what? Now I think I know the answer to this one. Without a SQL database in front of me, I might get it wrong, and it depends on the syntax. But I believe you would actually indicate drop column. So instead of writing table, you write column, and then you pass the name of the column, and then you would additionally write from table. So it would incorporate some of the DML syntax into the DDL executable. So here it would be drop column customer name from table customer. And sort of these more complex or compounding statements is really where the SQL syntax of the particular DBMS comes in how you want to execute those. Did that answer your question? Great. But good question. So as I was saying down here, the constraint is another SQL keyword which implements a new object, which here is customer PK, and this is a constraint object. And we're implementing a primary key on the customer ID. Now I'm confident that when you did it this way above, when you actually created the primary key in line with customer ID, it creates in the background this similar customer PK constraint, but probably uses some sort of auto naming procedure. So you may have to actually look up in the database schema what the name of that primary key is when you create it automatically. Yes, this is now coming back to me. The reason that we're doing this alternative fashion is this is how you actually have to create a primary key when you have a compound primary key. So for instance, if you had when we go back and we get here eventually, but if you look at the order table, I'm sorry, not the order table, the order line table, the primary key is a compound primary key. So both the order ID and the product ID make up the primary key. So it's a composite key, and the way that you actually implement a composite primary key is you create this primary key attribute, and you pass in two values under the primary key. So it would be custom for the order line. It would be order ID, comma product, I believe. Yes, order ID, comma product ID. So this is the way that you implement primary key constraints on a composite primary key. Okay, so we're going to talk about a few additional SQL syntax commands, especially while creating databases. So product ID here is, again, not null. This is nothing new. So we're looking again at the product. Now we're looking at the product table. Let's see if I can do it really quick. This will help anyone that needs to look at it. I'm actually creating, oh no, that's not the one. Here we go. This will go here. Okay, so for reference, we're now creating the product table. So here we have the product ID, and again, it's a 10 length char. So char here and not null. So we're not actually creating it as a primary key quite yet, but we're indicating that it cannot be null. Additionally, product name is a variable character or a string of length 30. And in addition, it's similarly not null. But now notice there's an additional keyword. The word is unique. Now, uniqueness is not something that we've outright spoken about, but we've discussed, and it usually pertains more to primary keys. But in this regard, product name is not going to be a primary. It's not going to be a primary key, but it does need to have unique values. So these were also called candidate keys, and candidate keys are similarly unique for every instance of an attribute, but are not being used as the primary key. So here, if product ID is going to be the primary key, and product name is both not null and unique, it is a candidate key, and it's in a one-to-one relationship with product ID. So for every unique product ID, there is a unique product name. So that's what the unique keyword is doing. Next up, we have the product description. Now the product description is going to be a variable character of length 100, so it's much longer. It can accommodate a lot more text, which is why we're passing the value of 100. Similarly, it also cannot be null. And not null, as a reminder, means from the ERD phase of this course, not null implies that it's a mandatory attribute or a non-optional attribute. Additionally, product price is a new data type that we haven't seen before, and it's called decimal. Decimal is a value that has effectively decimal points. So this is used commonly for currencies or for values that have many digits after the place. So here we're indicating that 6 represents the I guess how many places is that? You can have 6 characters, so tens, thousands. You can have up to 1 million in the first part of that function decimal, and in the second part, it implies that you can only have up to 2 decimal places. So a number which is something like, for instance, this is perfectly valid because we have 1, 2, 3, 4, 5, 6, exactly 6 in the front and 2 in the back. However, something that might be like this, pardon me, would not be valid because there are more than 2 decimal places beyond that value. So it would throw an error if you try to input this into the database. And then lastly, this would also be invalid because you have more than 6. Oh, you have exactly 6, I'm sorry. So this would be invalid. So here you have 7 places before the decimal, which is more than the 6 that's indicated in the actual constraint for that data type. And then lastly, this is similarly not null. So that means that every product has to have a price in this database, in this table in this database. And then lastly, the product finish, we're actually putting here this additional thing called check if the product finish is in cherry, walnut, or oak. This is a unique thing that I've never personally used, but it's effectively putting a business constraint on the fact that there can only be 3 values that a product can ever have. And those being cherry, walnut, and oak. This is a very strict constraint, and it's implemented again via the check logic. This would come into play when we had, if you'll all remember from my lecture, the LeBron James constraint. This would be one way you could actually implement that. Would say something like LeBron James has to have played in that game. You could implement it via some sort of check logic. And then lastly, we're doing again the constraint, which we saw on the previous slide for the customer table. We're going to do it here again. So we're going to constrain that there's a new object called the product primary key or product underscore PK, which is a primary key object, and it's being implemented on the product ID. So the product ID, which was already not null when we created the table, also now has a new constraint that it's the primary key of this table. And as my notes indicated, back on the check logic, the check makes sure that when inserting a new record, the value for that field must be in that set, the set being passed here. And then similarly, the unique constraint makes sure that the product name does not duplicate or has a unique value for every instance of that table. So it's a candidate key. Okay, now the fun stuff. How do we start defining foreign keys and default logic, right? I alluded to this earlier, but you know what, let me do the same screenshot. We're focusing now on the customer order table, okay? Bear with me a quick second. I'm going to bring the table onto this slide. Great. Okay, so now that we're looking at the order table, there are 3 particular attributes that we want to implement into this table. So we have order ID, customer ID, and order date. Now you'll notice here we have the same 3, right? Order ID we're defining as not null. We have order date, which is a new data type called date time. This is what's commonly known as a timestamp, and specifically in most DBMSs, date time will be in a format like year, year, month, month, day, day, hour, hour, minute, minute, second, second. I can write that down, but it looks more like this. So date time will look like year, 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 dash, month, month, dash, day, day, hours, minutes, seconds. And what we're doing here is we're saying default, another SQL keyword. Default, we're using a function. This is the first function we've really seen, but the function here is something that will return the exact timestamp of when the data is being generated or inserted into the table. So here we're inserting data, and it will use the system-generated timestamp. So for instance, if you're using a server that's located in another country, you might realize that when you use the get date, it's actually using the local server time. So those types of things, sometimes that globalization of enterprise infrastructure can lead to weird things like, oh, the customer is in EST, but the value is in, I don't know, Greenwich Mean Time, GMT, or UTC, and suddenly we can't figure out when this order actually occurred. So common problem that I face personally is reconciling timestamps. So just something to be aware of. And then lastly, we have customer ID again, which was char 10. And you'll remember that when we created the customer table, that was the same data type and length that we had. Now notice here that customer ID is not null, which means that it's a mandatory attribute. And again, it's important that you create the customer ID as char 10 here, and it has to be the same character length and type. I'm sorry, the same data type and data length as it exists in the table for which it is the primary key. So here, again, we define it to be char 10. So it's important that we define it here as char 10. Next up, we're going to have a constraint where we've defined the order primary key again. So we have this new object, which is a primary key object, order PK, and we're implementing it against order ID. So the order ID is now the primary key. And we're going to implement a foreign key object. So notice how in our earlier statement we had primary key. Now we have new keyword, which is foreign key. And it's creating an object called order_fk, fk being short for foreign key. Next, we're actually indicating which particular value in the table that we're referencing now, so the customer order table, which column in the customer order table is now the foreign key, and that's customer ID. Now what's important here is you can simply indicate that something is a foreign key without relating it to another table and indicating where it is the primary key. This operation will fail. So remember that a foreign key is a value in another table which has it as a primary key. So here, SQL DDL uses something called references. And the references keyword tells it which table. So here it's the customer table. And inside the parentheses, it's the column in the customer table that acts as the primary key as a reference to the foreign key object here. So again, order fk is the foreign key object in the customer order table implemented on the attribute or the column customer ID, and then the customer ID in customer order table references the customer ID in the customer table. Great question. So there's a question, what happens if we define in one table the order ID to be char 8, and in another table the order ID to be char 10? I believe either one of two things will happen. One, you will not get an error, but when you actually go to join on these values, because of the way that char sort of does leading values or leading padding, these values will be unequal. So if you, for instance, you have order ID 10, the value is actually space, 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 space 10. But if one of them is char of length 8, there will be a different amount of space paddings between the customer ID in the customer table and the customer ID in the customer order table. So it's important to really just maintain integrity because for me, half of the mystery of databases is unexpected outcomes. So if you're not diligent in naming procedures and labeling procedures with respect to metadata or schemas, it's just as dangerous for the DBA or the analyst not to fully understand the outcome as it is for them to get just an error or a bad outcome. Because if you don't fully understand why something is doing what it's doing, that means that you might be, I guess, inclined to draw bad results. So for me, I don't necessarily know what would happen if I joined on two attributes from different tables with different length characters. I don't know. And the fact that I don't know indicates to me that this could be problematic, either depending on the DBMS or depending on the way that these join, something that we'll learn later, but join criteria. Did that answer your question? Great. Okay, so I want to reiterate, because this is really important about foreign keys. In order to create the foreign key constraint, you're going to, again, pass the actual attribute that exists in the table that we're developing, so the customer order table. We're going to pass the customer ID, which is the foreign key, creates a foreign key object called order underscore foreign key, which references being a SQL keyword, references the customer table and customer ID attribute in that table. And recall that customer ID, when we created that table, customer ID is the primary key. And please be aware that all of these create statements can be transposed directly into SQL Server. So you're looking at SQL Server syntax. I cannot guarantee anything about Oracle or any other database management system. Okay, now for the last one. We have the order line table. Recall that the order line table has a composite primary key of order ID and product ID. And there's a very good reason why we're doing this last. We're doing this one last because in order to implement a foreign key constraint, the primary key had to have already existed in the associated table. So we couldn't have created the order line table without having already created the order table, without having already created the product table, because both of those are foreign keys in those tables for which they are primary key. So here, now that we've already created the order table and the product table, we're ready to create the order line table. So we have three particular fields that we want to create. We have an order ID, a product ID, and a quantity. Quick second, I'm going to just blow my nose. Pardon me. Okay. So again, we have an order ID, and we want to indicate that it's a char 10, and it's not null. Product ID, also char 10, also not null. So remember that these two already exist in two other tables. So we want to make sure that the same values are being passed when we implement them as foreign keys here. And then lastly, we have quantity. Quantity is going to be of type integer. So again, this is a non-decimal value or a whole number value between negative infinity and positive infinity. We're now going to add a primary key constraint, and we're actually going to pass it two values. So the only thing that's changed in the way that we're identifying this particular type of primary key is that in parentheses, we're passing two values, order ID and product ID. Now, it does not matter which order you would put them in. You could have done product ID, comma, order ID, or order ID, comma, product ID. Does not matter. There are times when these types of things will matter, but for here, it will not matter. And now that you have a composite primary key, we want to indicate which of those particular values are foreign keys. So when you have foreign keys, it's important to actually identify, I'm sorry, let me repeat that. When you have multiple foreign keys, you want to identify which particular, I guess, column name that foreign key is relating to. So here, you don't want to just create orderline underscore FK. You want to say orderline underscore FK underscore product ID. This is the new foreign key object that you're creating on the product ID. So again, foreign and key are two SQL keywords, which implements this foreign key object on top of the product ID, which exists in the orderline table. And this references the product table and the product ID, which is the primary key of that table. Additionally, you want to constrain another foreign key, which is the orderline underscore FK underscore order ID. This again is also the foreign key. I'm sorry, this is the new foreign key object that we're implementing on top of order ID, and this references the customer order table, and the primary key of that table, again, is the order ID. So this is how you create a foreign key. And specifically, when you have multiple foreign keys, you need to be very diligent about your naming conventions. So here we're naming it as product underscore product ID underscore order ID. And then lastly, we're also saying that these two values or attributes are acting as the composite primary key. Now note, there is no keyword for composite primary key. It's simply primary key with comma separated values inside of the parentheses. Okay, now that the tables are created, how are we going to populate them, right? How do we get data inside of them? If this was a regular class, I would ask, does anyone remember what the DML is for actually loading data into a table? I would give a quick pause. And then I would say, that's right. We want to actually insert data into a table. So we've now moved, and I'm going to go back a couple slides. We've moved from DDL, which is creating, altering, and establishing. Now we're going to move to DML, which is populating the data, deleting the data, and querying the data. So this focuses on data. This focuses on schema. DDL focuses on schema. DML focuses on data. So now that we have tables that exist, we want to create strong, we want to put data into strong tables first. I would then ask the class, why would we want to put data into strong tables first? Sort of the same reason that we wanted to create tables that did not have foreign keys first. Tables that are strong, relationships first is because there won't be any constraint on whether or not a particular foreign key value exists in the primary key table yet. So recall that you cannot have a foreign key value in a table without it already having been inserted into the table for which it is the primary key. An example of this might be in this schema that we're looking at here, right? You can't insert data into the orders table for a particular customer until that customer exists in the customer table. So the order of operation here again is you want to insert data into the customer table, then the product table, then the order table, then the order line table. Now, customer and product, that order doesn't matter, but these two have to happen first, and then order line. Because again, order line has foreign keys that relate back to order and product, and you cannot maintain the foreign key constraint of having the associated data point exist already as a primary key without first having loaded it into those tables. Okay, so first you have strong tables, then you have weak tables, and even the weak tables can have their own determinate order. So for instance, the order ID table, the order table should be loaded before the order line table because the order line table depends on the order table. All right, how do we get data in this stuff, man? How do we do it? And we use a command called insert into. So this is now it's called DDL, which is data definition. I'm sorry. Oh no. Am I getting it wrong? We are now doing DML, data manipulation language. Sorry, I got sick brain. We're doing DML, data manipulation language, and that's how you insert data into a database. So specifically, this DML command, insert into customer, and then here are the values. Values is again another keyword. So here we do not specify the column names. There's one inherent flaw, which may not be immediately obvious, but this assumes that you already know the order of the columns in the table. So here we're assuming that you know that the column here is the customer ID, and here is the customer name. However, maybe you got it wrong. Maybe you don't remember. Maybe you don't want to have to go look it up. If that's the case, then you can actually specify the specific columns in the insert into. So here we're inserting into customer, and here are the values. Again, it ends in a semicolon. here we're now going to, below, we're actually going to do it optionally, which is insert into customer. Then we're going to indicate exactly the same order as our data, what the particular the columns are that we're inserting data into. So here we're indicating, in reverse order, mind you, the customer name and the customer ID, and we're inputting those values as Upstate Medical and C1802. So here, in this way, by discretely articulating the column names, you don't have to memorize the order for which you created the columns in the first place. So this is a nice trick to not having to remember to do so, to getting it wrong. Because, for instance, if you had done Syracuse C1100, it might actually not break it. Now, I know that it will break it because of the way that we defined the data types, but had we not defined the data types the way we did, you could have inserted the data into the wrong columns, and then you would have probably a, bad database, or bad table in a database. Okay. This, again, is now my favorite part. We're going to talk about selecting data, getting data from tables, either to solve problems, to support an application, to support a website, or simply to move data from one place to another, ETL. So we have the common select, which is another keyword in SQL. Star, which means select every column or every field. From, which is another keyword, and it indicates the object that you're querying, whether it's a view or a table. And here we're indicating the table customer. So in DML, data manipulation language, you always need to indicate the type of object. I'm sorry. In DDL, in data definition language, you always need to identify the type of object that you're defining, whether it's a table, a view, a stored procedure, an index. But in DML, data manipulation language, you do not need to necessarily indicate the type of object. And it has to do with, usually you can only query or delete certain types of objects. So it's assumed that you're not going to select from a stored procedure, or you're not going to delete from a view. But in cases where there are conflicts in naming conventions, you can also you can do prefixing, and I think we cover that in the next lecture. So here, we're selecting all of the columns from the table customer. So this would return to us both the customer name and the customer ID and all of the values associated with it. Here, we're now going to select only the customer ID, so now we're going to pass it a specific column or field. And we're indicating the same table from the customer table. So this will just return a single column, which are all of the customer ID values for the customer table. And then lastly, we're going to actually delete from the customer. So delete from customer is actually going to delete all of the records. It's going to delete them all. Now, this is different than dropping the table. Dropping the table means that the table itself, the table object, does not exist in the database anymore. Delete from customer means that all of the data records from the table will be gone. However, the table object will remain. It will simply have 0 records. That's the difference between the delete command and the drop command. Delete is data manipulation language. Drop is data definition language, DDL. Okay, now we want to do another type of command, which is the check command. So let's first look at inserting data into the products database. So here we have I'm sorry, I keep saying database. I mean table. I'm sorry for that. Insert into the product table. Here are, again, the keyword values, indicating that these are actual data points that we're going to put into the table. So again, here we have the product ID, product name. What is this again? I forget what this is. Oh, it's some other additional value that was not previously defined. And the product price, and then the product color. However, then we're going to test the constraint. So insert into product values. This is all the same, except now ash is going to throw an error. Because if you recall, the way that we defined this, we had a finite list or an array of values that this could possibly be. It can either be cherry, walnut, or oak. And that was the way that we actually defined this. Oh, by the way, it was product description. That was the one I didn't know. Product finish, it has to be cherry, walnut, or oak. So if you try to actually execute this command with ash is not in this list, so it will throw an error. And this is how you actually restrict particular values from not being ingested into the database. So what we actually do here is we insert into the products, we fix it. We say, oh, let's just do cherry. So this was not actually implementing anything new. We're simply testing that earlier check command or check constraint that we implemented when we created the table. So here we checked whether or not ash would load into the database. You could do this on your own, but you'll notice that it does not successfully load into the database. So what we have to do is after we see the error, we fix it and we write cherry, and we're good to go. Okay, now that we have all our strong tables defined, our strong tables again being the products table and the customers table, we're now going to first populate the customer order table. The reason that we're doing the customer order table first is because, as I mentioned earlier, the customer order line, the order line table depends on the customer order table. So we have to do any table that is a dependent, or any table that's a dependent of another has to come second or later. So inserting into the customer order, we have both the order ID and the customer ID. So again, here we're articulating exactly which columns we want to insert the data into. Instead of just indicating any old column, we're saying for the order ID and the customer ID, here are the two values that we want to insert. Additionally, we want to do the same thing below. The difference here being now that the order ID is slightly different and the customer ID is the same. Again, these act as a pair of, do these act as a, no. Order ID is the primary key. It's not a composite key in this instance. Okay, now what's going to happen here is because the customer ID is a foreign key, the customer ID must already exist in the customers table. If it doesn't, this will throw an error. So if you had C11100002 or 8, and it doesn't already exist in the customer table, it will throw an error because you've violated the foreign key constraint on this data point. This data point for customer ID here in the customer order table being a foreign key constraint. All right, if you then select from the customer order table, you'll notice that you get an additional field, which is order date. Now remember that you didn't actually insert order date when you inserted it into the table. Notice here it's not indicated. That's because it had a default value. The default value, again, was using the function system date or get date. I don't remember exactly. Yeah, it's using the function get date, which returns the system generated timestamp. So when you actually query the data, that default value will now persist in your return clause or in your return statement. And then if you decide that, you know what, I need to go back and change that value, that default value, that's perfectly fine too. Default only means that if you don't give it an explicit value, it will use the default one, but you can override it by actually explicitly articulating what value you do want. So here we're going to insert a new customer order and indicate exactly the date that we want to insert. So here we want to insert October 23rd, 2015. And again, we want to do it again down here. This was, and I'm sorry, and this last line indicates that C10003 does not exist in the primary key in the customers table, therefore this would throw an error. So the two takeaways here are you do not have to indicate default values. You can override them by passing them as values here, like so. Remember that if you override the default value, though, it still has to be of the same data type that you've indicated in the column. So here the column is date type. Now notice that you didn't articulate, I don't know, hours, minutes, and seconds. Usually date types are pretty flexible. So here, it would probably just assume that the hour is 00, the minute is 00, and the seconds are 00. That's very common with respect to dates versus date times. Okay. Sequence of deleting records. Now that you've deleted now that you've inserted new records and you inserted them into in the order of strong tables first and then weak tables, and you do that in order to maintain foreign key constraints, you want to back out or delete rows in the exact opposite ways. You want to first delete instances of where that value is a foreign key, and then delete it out as a value as a primary key. And you want to do that because if you deleted the primary key first, you would then break the foreign key constraint on the table that you have not yet updated, and you would throw the database into an inconsistent state. So you want to first delete from the weak table, which is the one that has the foreign key, and then from the strong table. And then lastly, we have the last type of data manipulation clause or command that we're going to focus on today, which is the update. And if you recall, as I defined earlier, the update statement takes a value that already existed in the database and replaces it or changes it without moving the row. So for instance, if you wanted to change all of the values of cherry into ash, you would say update update product set color equal to ash. And that would update all instances of, here it would actually update all instances of the color to ash, but you could put sort of if-then logic. But we'll get that next week. It's a little bit more complex, but it uses something called a case statement. But update records here, update records are perfectly fine as long as it doesn't break the foreign key constraint. So you cannot go and update a foreign key to a new value for which it doesn't exist as a primary key value in its origin table. So for instance, you can't suddenly update customer ID to something that doesn't exist in the customer table. Oh, there's another one, and I kind of forgot about this one. Okay, so alter table is a data definition function which allows you to add new columns or change the data type of the column in the event that you realize, oh, the data type that I anticipated is not what I'm seeing or getting, so I need to make a change. Or, hey, there's a new piece of data that I didn't anticipate, but I would like to incorporate into my data schema. I need to create a new table and give it a data type. So here we're saying, and again, this is a good test. You know that this is a data manipulation language. You know that this is a data definition language command because you have to articulate the object type. So we're saying alter table customer. Now a new command is add. Gender is a column name, and you're indicating that it's a single character. So it's a length of 1. Here would probably be M for male, F for female, and then any other character for any other gender that someone specified. And then lastly, to remove an existing column. Oh, so Chi, here's your question from earlier. So this is how you drop or delete a column in SQL Server. Again, I'm pretty sure this is different depending on the DBMS. But here, if you wanted to delete a column, you actually say alter table, indicate the table, and then you drop the column gender. So again, it's using the drop command, not the delete command. All right, great. So as we go through, we're going to take a look now at sort of creating an auto-generated number using identity. Now, in Access, I think this was called auto number, but this is a good example of creating surrogate keys. I know that surrogate keys was a really big focus during, I think, lecture number 4 when we were talking about identifying versus non-identifying relationships. But the identity function in SQL is how you can actually identify these things. I have a quick question from Min Yang. Let's see. how to determine the place where to add the new column. For instance, add a new. So I'm pretty sure when you add a new column, it's always going to add it all the way at the end. So for instance, when you added gender, I think that it automatically adds it at the end of the table, which is why it's sort of dangerous to automatically ingest new data without indicating the columns that you're putting each data point into. But there probably is a command that allows you to change the order, but it's not one that I'm familiar with. It's not very common. Or if it is, it's not something that I myself am all that familiar with. But we could definitely do some research using W3 School. So there probably is a format command. Now, Chi, is there a question around format as a command? I'm not sure I understand your question. Okay, Chi, we can take it offline after this if that's okay. I just want to kind of, how many more slides do I have? About 5. I want to get through this and then we can pick it up tomorrow as well. So creating a primary key that is auto-generated, and it's using the identity function. So here we have the student table, so this is a totally different schema. So the student ID here, we want it to be an integer value. Excuse me. Okay. And this is important since the identity function is going to create an integer. You need to indicate that it is an integer value for which you're creating. So the student ID, which you want to be a surrogate key, you're going to indicate that it's an integer data type, and you're going to use this thing called identity. Now, identity has 2 parameters. The first is the point for which is going to start incrementing. So, for instance, if you have identity 1 comma, means that the first value that you insert into this table will have the value 1. The second data record that you insert will have the value 2. The third will have the value 3, and so on. Now, you could start this at 1,000. So the first student ID would be 1,000. The second student ID would be 1,001. And the second parameter in this formula for identity is the number by which you want to increment. So for instance, if you wanted to increment by 1 or 2 or 3, and that would indicate whether or not you want to whether or not you want to go incrementing by a single integer value or multiple integer values. Then that's really it. That's all that this is doing, this identity function. And then additionally, if you want it to be the primary key, you can indicate that here. But if you also recall, you can do that by creating the constraint. You create the primary key object, and then you pass the table and column as primary key values in the statement. All right. I'm going to skip this slide. I don't think it really offers that much. So I think the rest of this is really just focusing on actually implementing this stuff. So I really want to thank everybody who's on the call. I'm going to post this to Blackboard once I'm done. I do apologize for any of the cold-like symptoms that I kind of displayed on this call or this lecture. Obviously, I'm a little ill, but hopefully it's clear and concise. And I do apologize for any DML versus DDL hiccups that I had. I would have gotten it right in class. I think I would have. Otherwise, we're going to meet at the same time tomorrow at 7 p.m. And we're going to cover SQL actually executing commands in the database. So a lot of what we covered here, we're going to focus on tomorrow in the database. And then lastly, if you're interested in the slides, there is a program that would allow you to actually create an ERD, and then it will create automatically the scripts that you can implement against the database, and it will create the schema for you. So all of these primary key, foreign key constraints, all of these data values, as long as you articulate them in the ERD, it'll create the scripts for you to actually execute them and create them in the database. So this is pretty neat. It's not an obligation. This is more optional, but something if you were interested, you can check out. Okay, that's going to do it in terms of the lecture. I will see, hopefully, at least some of you tomorrow at 7 p.m. on Wednesday, October 10th. Great. Thank you so much.